Thank you. So after plus 15 years, this is how far we can take it. Talking about 15 years, we're not going to talk about me, but does any of you recognize this? This is kind of talking about me because this is talking about my age. This is the Commodore 64, which we used to play with when I was a teenager. And when I think of what we could do, what kind of magic we could do with this thing, I can't help thinking of what could we achieve if we had the possibilities that we have today and the time we had back then. And this is kind of what drives this talk, because I wanted to show one of the easiest way to make digital products. And there's a pretty fine overlap with that and Arduino, because what originally defined the Arduino project was the wiring platform done by a Colombian student in Italy back in 2004. He wanted to make a little package with hardware and an IDE so that everyone could make digital products. 1 year later, someone took his work, replaced a bit of the chipset with a cheaper chipset, and open sourced everything. And that was the birth of Arduino. And by the way, the name Arduino, that happens to be the name of the cafe where the little crowd met when they did the thing back then. Arduino is open source. And probably because of that, it has a huge community. And it's used throughout the world for educational purposes. And it's so easy to get started. So let's start, and we really start with the basics. This is an Arduino board. In real life, it could look like this. Little thing. Let's take a look at it. If we take a look at the upper part of the picture here, we see a row with some connectors, some pins. This is digital I/O. At the bottom, we see analog pins, and then there's a USB connector and a power connector. It's pretty obvious. The USB is for programming the thing, and as compared to the Commodore 64 that lost everything when we turned off the power, this has flash memory. So when we upload the program to this thing, it stays, which means then we don't need the USB cord anymore. Then we can power with the power plug afterwards. Arduino is, as I mentioned, it has a huge community. And you can find extensions for anything. And I really mean anything. And if some of you is thinking about some weird thing, you could probably not find an extension for that. Yes, you could. You can find extensions for anything. We call them shields. You can find a shield for anything with the Arduino board. Let's get started. And this talk is going to be good, old, plain code. No rocket science, just code snippets. Please keep that in mind when you vote. To program the thing, we download the IDE. This is not a real rich IDE as we know it from Visual Studio or Xcode or IntelliJ or whatever. It's more like an advanced editor with syntax highlighting and with a compile button. But this is what we have. Let's see what we can do with it. Let's make a Hello World program. And somehow, all Hello World programs in the Arduino world control pin number 13. And the reason for that is quite simple. Pin number 13 is hooked onto a little lamp on the PCB, so it's pretty easy to see if the things work. We'll do the same thing here. This code snippet, well, this is our Hello World. At the same time, this shows the pattern for all Arduino boards, or all Arduino programs. No exception to the rule. Everything follows this pattern. So there's a setup, which, surprise, is being executed once, and then there's a loop. And there's no timing in the loop. It's just being executed over and over again. And this is what the Arduino can. Setup and loop, nothing else. Our little program here, well, today we will work with pin number 13. We configure that. Remember, the upper row of the pins, they were digital input, output. So today it's an output. We've configured that in the setup method, and in the loop, we pull it high, wait a second, low, wait a second. And just because this is deep down simple, let's see how it works. So this is the result. Marvelous. Let's see how far we can take this. Let's make Hello World part number 2. If we take a look at those connectors, we see there's an RX and a TX. There's a serial communication thing on the board. If we don't do anything with these 2 pins, they are, through magic, hooked up to the USB port. And the Arduino IDE has a little terminal. So we can actually use that as a screen, which we do like this. And it's pretty simple to do so. I just extend my hello world here. See the line in the setup, serial begin with some port speed. And down in the loop, I write something high and low. And we probably recognize the syntax, print and print with a line shift. And if I open up the terminal, this will be the output. So we can actually do some debugging too, not only with a lamp that we can turn on and off. And as you may have seen already now, programming is C. This is C syntax. In most cases, you don't have to think about, say, the more hardware-specific parts of C, addressing memory, doing pointer, dereferencing pointers. Everything is, in most cases, shielded away or kept in structs or, well, some method call-ish things, library functions. Let's go one step further. See, my screen has an input field too. My serial communication, well, it had an RX and a TX, so of course we can do things both directions. So this is what we can do. In our setup, once again, we configure the serial channel, and as long as we have something available, we read it and print it. So this little code, in fact, does nothing but whatever you type in the input field is echoed in the output area. Or we can do it a little bit more rich. Rather than reading character by character, we can work with entire strings. And this is where parts of the C libraries in the Arduino gets a bit more advanced. Once you actually work with strings, not with character buffers, as you would do in C. There are libraries for everything. It is C, but something is shielded away. Let's see what else we can do. It has inputs. And in the Arduino world, you don't need pull-up or pull-down resistors. And I know only hardware nerds, as I, would know what that means. So let's just take a very brief look at it. See this very simple figure here. Let's say we have an input on the Arduino. And I want to do something with that when that input goes low or high. But until then, I don't want to do anything. Now the thing is, on this microcontroller, everything that has a voltage below 1.45 is definitely low. And everything that has a voltage above 3.3 volts is definitely high. But in between, you don't really know what it is. It could be anything. So if I would make an input that just reacts when we go low or high, and until then it just floats, it's not hooked up to anything, I really wouldn't know what state it would be if it would be low or high. So in this situation, until I close the switches, I actually don't know the electrical potential of the input. Which is why always, when you're working with digital I/O, you use pull-up or pull-down resistors. Because when the input is inactive, through that resistor, you can determine if it should be high or low. Always, almost always. Because this is so always that it has been done for us in the Arduino world. So dealing with digital input, you don't have to solder resistors onto it. Let's see how it works. What does this program do? Well, in the setup, it defines a pin for output. Then it defines another pin for input. And it writes that input high, means it pulls it high. It mounts a pull-up resistor to that. And then down in the loop, I read the input, and if the input goes low, I turn on my output. Or else, I turn off my output. So in fact, this program, it reads an input, and if the input is high, the output is low. If the input is low, the output is high. This is what we do here. Stupid example. Let's see what more we can do. What does this program do? Stupid question number 1 of today. Sometimes the questions are so stupid that you don't even dare to answer it. It turns on an output, waits for 5 milliseconds, turns it off, waits for 5 milliseconds, and then it repeats. What is the result here? The result is that half of the time the input is high and half of the time the input is low. So on the average, it's somewhere in between. And if low corresponds to 0 voltage and if high corresponds to 5, then this means that on the average, the output is 2.5 volts. We call this pulse width modulation. And this is in fact supported by the Arduino. So you can do analog output with the Arduino. If you take a look at some of the pins, you can see some of them have a little mark. Those pins support this analog mode. It works like this. So I define my output. Any number between 0 and 255 defines the analog level of the output. Okay, or the pulse width of that square. This is brilliant because now I can realize part of my use case. As you may know, our company, The Perfect App, makes some app tool. And this app tool can draw a curve of the number of active apps out there right now. I want to make that curve with a laser beam. And for that, I need an analog signal. I want to have a mirror that can reflect a laser beam. And by moving that mirror, I can draw in 1 dimension. If I could have another mirror moving in the other direction, I could draw a laser beam in 2 dimensions. And for controlling a laser beam, that would be the thing. And don't laugh. If you think of a loudspeaker, it's actually very, very accurate. If you think of what it's able to reproduce, it has a very, very fine resolution. So that would be the thing to use. But of course, this is not some brilliant idea that I just got here. This is a pretty common thing that you want to reflect a laser beam with a loudspeaker. In fact, it's so common that you can buy a thing like this. This is in fact a loudspeaker meant for this, for the purpose. So this is what I'm going to do. I'm going to use 2 analog outputs to control those 2 mirrors to be able to draw a laser beam in 2 dimensions on the wall. And just to make everything very clear, this is the physics. Let's make a little experiment here. So if I have a full range in both directions, 0 to 5 volts, that means for my very first test, if I can apply 2.5 volts to each coordinate, the beam should be in the middle of the total working area, right? So in the Arduino world, it would look like this. 2 analog outputs, and something in the middle of 0 and 255 as a value of each one of them. Let's do so. And this is my result. I expected to see a laser beam right in the middle of the working area, and this is what I got. So that leaves me with 2 choices. 1, it's goodbye to Laser Beam Incorporated, or 2, I need to learn something more. I don't like any of those choices, but if I should pick, let's learn something more. First of all, why is it that we see this? Well, this is in fact because, yes, we support some kind of analog signaling with the Arduino board, but the frequency is very low. It's actually at 500 hertz. So what I had on the picture was actually all the lows and all the highs, and then the movement between. We need to learn something more. Let's dive further into the Arduino world. Analog inputs. There's a number of inputs named A0, I think it starts with A0 to something. This is how we control them. They work this way, that a signal between 0 and 5 volts on that input pin is converted to a number between 0 and 1023. So look at this. I define an input and one of those outputs that can actually act as an analog output. I read the value of the input using the map function. I map the value of the input to something that I can print on the output pin, and I print it. You know, for lamps and everything, it would be perfectly fine to use those analog outputs because you cannot see that it flashes so quickly. So this, in fact, it reads the value of an analog input, and it reproduces that value to the analog output. These are the basics: digital I/O and analog I/O. And frankly, everything we've seen so far, we could have done that with a wire and some soldering too. That's not very advanced. Let's take it one step further. This little thing here, it's a little temperature measuring thing. It works this way. You apply 0 to one pin, plus 5 to the other one, and on the middle pin, you can read the voltage, a voltage that is dependent on the current temperature of the thing. Or to put it another way, a voltage, or the temperature is reflected through a voltage between 0 and 5 volts. It works like this. So, in my loop, I read the temperature. The temperature reads the value of the analog input. Remember, that's a value between 0 and 1024. I convert that into the voltage. I know that it has an offset because it can actually measure negative temperatures. And forgive me, I know we're scientists. There probably is no such thing as a negative temperature, but measuring in Celsius, yes. So I convert the voltage into a temperature, and I print that. which looks like this. In this little example, I had my fingertips on the thing, so I tried to heat it up with my fingertips. So you can see the temperature increases. And then I let go, and the temperature starts to fall again. And look, somehow, though I have a number of digits, somehow it fell back to the exact same temperature as it reached on its way up. This kind of shows that, yes, it is an analog input that we read, but it has a limited resolution. A number between 0 and 1023 is in fact a 10-digit resolution, 10-bit resolution. This is what we see here. It is some kind of limited. Does any of you know about the PC open source project called LCD-Proc? It was around 10 years ago. Now we're back to my age too. Yeah, I can see you know it. Yeah, there was this display, Hitachi display. This is the most common display in the world. You see that everywhere, on the coffee machine, on whatever. Every time you see an LCD display, this is the thing. This is a standard. Back in the days, there was a project, an open source project for Linux and Windows, where you could control this display using the serial port or the parallel port, which were common on PCs back then. Of course, this display is supported by Arduino too. And it takes very, very few lines of code to actually use the display. You can see on the bird's nest here that I have a couple of wires. Those wires basically mount the data pins to the display and a couple of control signals. And this is what I do here. I include the library liquid crystal. I make a variable, define it with the outputs that I intend to use today, and then I can print on the display. This is all it takes to print on a display like this. And the result goes like this. Now we can start to do more advanced things, because now we can combine things. So in this case, I read the temperature as I did before, and then I write it to the display, which reveals another thing. See, it's actually more than a display, it's a screen. It even has a cursor. It has a print position. You can see that in the middle of the slide here. I actually set my cursor position, the print position, back. And yes, there is a space after the string that I print, because it could be that I'm printing a shorter string that I had before, and then I would like to clear what's left. So in this case, I have a little thermometer like this, with like 12 lines of code and a couple of wires. Let's move on here. Think of serial communication. What is that? Well, that is, in fact, just some output, digital output, that you pull high and low at a certain pattern. And someone else can recognize that pattern, and then we can communicate over a serial channel. Which means that all input outputs on the board could actually be used for serial communication. This is what the library software serial does. It allows you to use any two inputs for serial communication. And a lot of extensions, a lot of shields make use of that. One of those shields is that one here. This is a GPS. And I don't know if any of you is familiar with the NMEA standard of GPS. That's another way of putting nonsense, NMEA. This one, the manufacturer told me that you can expect this to communicate on pins 3 and 4. So use the software serial library and you can communicate with this. And this is what I do here. I'm doing very, very little, but in the loop, as long as the GPS serial line here has something to tell me, I read it and I print it. And by the way, please note line number 5, the tiny GPS plus thing, that will become important later on. But this actually reads the stream coming from the GPS here. And this is what it gives me. This is in fact the raw data of an NMEA GPS. I have no idea what to look for in these numbers. Sometimes I think I recognize some coordinate there, but I don't. This is where this tiny GPS library comes in that you saw on the previous slide. Using the tiny GPS library, I made this GPS object. And with that GPS, look down here. As long as I have something to read, I pass it on to GPS with the encode method here. I do this for some time, and then I return to my main loop function, and now I can actually interpret what the thing had to tell me. So this is what it takes to print a thing like this, to actually read a GPS with an Arduino. And you can read all kinds of things, not only the coordinates, a lot of things. Let's move on here. There's a software project or a library called Wire, or the Wire protocol on Arduino. Using that, you can make something like a USB bus with the Arduino. Not serial communication point to point, but more like a bus, USB or a CAN bus or whatever you're used to. It has some limited speed and it has some limited address space. But you can actually use that to chain things in the Arduino world. The following example here is stolen without modification from the official Arduino web page. Look at this. In the loop, it starts to transmit to someone, whoever might be listening, at address number 8. Then it writes something, and then it terminates the transmission, and then it repeats. So this one just echoes out characters for whoever has address number 8 on the wire bus. This one is a bit different. In the setup, we tell the wire protocol that now we want to listen on address number 8. Then we register some callback method, which is being called whenever something appears for address number 8 on the wire bus. So this is what we do here. So this, in fact, reads what was transmitted by the previous program and prints it out on the serial. So we can chain 2 Arduino boards, 2 or more. And the way we do it is just by adding a few wires. And please note, those wires are not crossed, because this is not point-to-point. This is not RX to TX. This is a bus, serial bus communication. This is very good to know, because then we can do things with higher resolution than just digital input-output. I Googled very short and found this digital to analog converter. It's very small. It's the size of my thumbnail, this little thing here. I want to use that to realize my use case. The vendor told me that to use this, you need to use the wire protocol. And then he gave me the library, this Adafruit MCP something library, and I can use that. So I set up 2 of these boards, 2 digital to analog converters with 2 different addresses. The vendor told me that too. You can expect those addresses to work in the setup method. And then I make some coordinates. And in my loop, I just continuously plot the x and the y coordinates out on the wire bus using the set voltage. See, everything has been shielded away or kept away from me. I don't have to think of this as C. They just provide me the library, and this is what it takes to print out a value to the little board that I got there. And this is the result then. Now it starts to look like something. So now apparently I can hope that it would be possible to realize at least the drawing part of my use case. But I also need to fetch the data out into my box here. So we need to learn something more. There are two places on the internet where you can find almost anything for Arduino. The one is Adafruit, which was mentioned on the previous slide with that little PCB. There's another location, SparkFun. You can find anything there. This is a Wi-Fi shield that they provide. It's pretty easy to use that Wi-Fi shield because, of course, they provide a library too. So, if we start down here, this is actually what it takes to configure that Wi-Fi shield to a certain network. So I can configure that to my network. And then I can start playing with it. And let's see what we can do. See. Now that I have it hooked on to the network, I can do TCP communication with that shield. I do that in the code line which the first arrow points to. See, I connect to some server on some port. I need to tell that for this to work, of course, we have set up a server somewhere. We have an HTTP endpoint that can provide me with the coordinates that I'm going to draw later on. This is not HTTP communication. This is TCP/IP. So I make a connection to that server, port number 80. And then I print a request to that channel, and I can read whatever comes back. So I can do HTTP communication like this. Very few lines of code. So how do we use that? Well, my idea is to just keep drawing points, and then from time to time, refetch the data set, and keep drawing again. So this is what I'm doing. Continuously loop through and draw points. Then each minute, should I fetch new data? If so, fetch it, and plot the new points for the next minute. This is how I'm going to realize my use case. Now we need to move one step back again and think of, okay, what I made before was a TCP connection, not an HTTP connection. So when I send my request, HTTP request, I get the entire HTTP response back, not just the body. Because this is TCP connection. I just happen to speak HTTP over that connection. So these are the bytes that I get back. I get the entire header and then my data. So I need to keep that in mind when I pass the data that I receive here. So this is in fact what I should do instead. So loop through and plot my points. Do it again and again and again. At some point, it's time to fetch the data. If I do so, I request the data, I get my response, I pass the data, and then I can re-loop. Which means if I want to continuously draw the curve over and over again, from time to time, I need to stop and do something else, fetch my data. So the drawing process would stop while I do this. This is bad time, what's marked with red here. This is where the wire protocol could come in handy again, because that allowed me to chain a couple of Arduino boards. We saw that I could define a master that could do things and send it to the slave. So here's my idea. I want to let the master request data whenever needed, and whenever needed, pass it on to the slave that should do nothing but just draw and draw and draw. Then from time to time get an interrupt, get new data, and then draw and draw again. So this in fact realizes my use case. This is how it looked on the web page. And this is how my curve ended up looking. And you can see I have some electrical noise here. I had to do this with a pretty long exposure time with my camera. And apparently there was some electrical noise that made it not very accurate every time I draw. But this is in fact the result of what I just did. Let's see if we can extend it a bit more. Though it works, we can do more. So what if we could, it seems that my mirrors are fast enough to do things. So if I could plot my curve, then take the beam down to 0 and drag it back, then I would indirectly draw the x-axis by doing so. And we know, or we've seen that it's pretty easy to do with code, whatever is needed to be done here. So we could actually make that even more advanced. We have digital I/O on the thing too, so why not turn off the laser while we move it, and only turn it on when we draw? So loop through the data points, turn off the laser, move it down, turn it off, draw the axis, turn it off, move it to the next point, turn it on, and then you can draw again. And this is pretty simple because we have digital I/O. The only thing that is not simple is to find a laser where you could actually do it, turn it on and off, and especially because I needed to bring it on the airplane. And the only thing I could find to bring on an airplane was this little pen here. And just because I couldn't help. I asked my daughter to write GOTO on some grid paper and then take all the coordinates and type it into an array for me. And you can actually see here, it is pretty accurate. You can almost see the grids in this. Let me show you something more. Everything I've showed so far was with the Arduino Uno boards, it's called. There's another board, the Arduino Yon. This one has not one, but 2 processors. One of them running a Linux kernel. This is the schematic way of putting it. It means that if you can come through this bridge, which is pretty easy, you can actually, from your Arduino code, execute Linux commands. And why is that interesting? Well, take a look at my GPS program that I had. Using the bridge library, see in setup, bridge begin, I can get through to the Linux part. Then I can actually look at, I include the process library up there. Then I can actually spawn a process and issue, for instance, a curl command. So rather than downloading and passing TCP traffic and HTTP myself, I could actually do everything with a curl command. by using this board that is a bit more advanced, which is a very easy way to upload things to. Just curl it up to whatever. This board that I have here with an antenna, this is in fact a telephone. It has a little connector for a SIM card here. This is a telephone. It even has jackets for earplugs and for microphone. The way you use this is what we've seen before. It's serial communication. Using the software serial library, you just start communicating with the thing. If it has something to tell you, you can read it, or you can just write things to it. And things you can write to a telephone, now we're back to my age again, is AT commands. So if you could just write the AT dial command, you could actually make this thing ring or send an SMS. There's an AT command for that too. So just by writing to the serial connector, you can do that. And if you take a look, follow that link, you can actually see how you set up GPRS communication, so network communication, using that board. So what have we seen so far? We've seen input and output, digital, analog. We've seen serial communication. We've seen a lot of things, but everything that we've seen is in fact a combination of those building blocks. And with that, you can achieve magic. And I really mean magic. Here's one of the projects that I'm working with right now. This is an e-ink display. I'm trying to see if that could be an extended screen to my phone. So I have a little Bluetooth extension and the display. And don't tell anyone, but this could be the future conference badge. And before we sum up here, I would just like to welcome you on stage afterwards to see the thing here. When I played with this back home, I used this as my laser. But I wasn't sure that I could get this on the plane. Oh, well, in fact, I was pretty sure if I could get this on the plane. So I decided not to try to. So here's my travel edition, which is not that advanced. And with these words, I wish you happy hacking, all of you.
Thank you, Preben. We do have time for a few questions. Any burning questions from the audience? Comments? Yeah.
Hi, and thanks for a great presentation. I understood as much that the digital to analog converter was to increase resolution, but I didn't understand where in the circuit you added them. Could you explain that?
Oh, yes. See, what the Arduino gave me right out of the box was an output that can produce a signal like this, but not very fast. This serial bus, the wire thing, runs at 100 kilohertz. So on that you can clock out those pulses very faster. And this is what the boards use. Did that answer your question? Not really.
Where in the circuit?
Where? I'd like to welcome you on stage here to see it. But actually, because this is hooked up to that serial bus, it's actually just 2 wires from the serial bus out to those little extension things that I bought. And from there, it goes to the loudspeakers, yeah, yes.
Very good. Don't forget to vote, by the way. Don't forget to vote.
Hi.
Hey.
Thanks for a nice presentation. I heard about another project called Raspberry Pi, which is also
Yeah.
for playing around. So what would be the difference and between those two?
I have no experience with the Raspberry Pi, but I know it's more powerful. So it can probably, or it can for sure, do things that you cannot do with the Arduino. But I doubt that it's so easy that you, with that few code lines, can do magic that you can do with the Arduino. Has any of you experience with the Raspberry Pi and doing things like this? Yeah. I mean, the Arduino, the entire Arduino environment is meant for this and nothing else. So everything has been, from a programming point of view, everything has been optimized for doing this and nothing else but this. And I think that's a big difference.
All right, I think that's a wrap. Thank you again, Preben. Give the guy a hand.
Thank you.